Hello and welcome to the podcast According to Sci-Faith, where we discuss topics revolving around the compatibility of science and faith. I'm Joshua Göcking and you're listening to According to Sci-Faith. Preview of the episodes 45 to 48, Quod, Erat, Demonstrandum, which was to be demonstrated. Episode 45, Mathematical Proof. If you remember your math lessons from school, if you just try to think back of it, you might it might have been that you really did a lot of computing, calculating, solving for x and these things. This if your school math was kind of like mine, then this would have mostly been what you have been used to. That there basically were tasks where you had to compute something, you need to solve an equation, you need to solve this equation for x or for some other variable, although most of the time it was just x that you need to solve it for, or different tasks, but most of the time it had to do with calculating, computing some values and so on. But if you are studying maths, studying physics, where also a lot of math is included, or some kind of engineering topic where this is included, then you will soon realize that this is not really what math is all about, that this is actually just the practical part of maths, and that most of maths is a lot more concerned with finding proofs, with finding mathematical proof to certain theorems. And if you look at a math lecture, for example, then you have basically this structure of a definition, a statement, and the proof of this statement. This is basically how it works. There's a definition, there's some theorem, some corollary, some lemma, something presented, and this is then proven. So, and most of this part is actually in the proof itself. So to prove this statement is a huge part of math lecture and of math itself. And in some cases you even need other statements to prove the statement that you are trying to prove, and for this there are these smaller statements or smaller theorems like lemmas or corollaries. And this is basically how you soon learn, if you start studying maths, for example, how this works. And there you see that to prove something is of huge importance. It's really important in math. It's more important than the calculations you do later on, because once you have proven these statements, then you can do the computations, then you can do the calculations. This is the part that in school oftentimes was skipped. You usually got these statements as a given fact, and then you would work with them. But actually in maths, it's the case that you start with some axioms, you start with some things that you say, okay, we believe that they are completely true. And then you make definitions where you define the terms you need to make your statements, the statements you want to make. And from these definitions, then you make these statements, and these statements, of course, they have to be proven. You need to show that they are in fact true given the axioms and the assumptions that you made. And this is the big part of maths, to really prove them, to really show that following the assumptions you made, that they follow out of them, that they can be concluded from these axioms that you have. And without this, you cannot come to the computing part, because you have not shown that what you are talking about, what you would then be computing, that this is actually true. So this is really important and really foundational work that you find there if you begin to study math. And therefore, if you begin this, you need to really learn how to make proofs. How can I prove something? If I have a certain set of statements that are proven to be true, or a certain set of axioms that are assumed to be true, and maybe some statements that I already have proven following out of it, how can I prove that such a statement or this corollary or something like this, how can I prove that this is indeed true? How can I do this? How what is a way to do this? And there are certain methods that you can use that have been developed by now. And in this podcast episode, I want to mention 3 of them. There are several more, but most of the time you really will use one of these 3 methods. They are the most used, and I cannot really think of any time during my studies where I used a different proof. Maybe I have, but most proofs were in one of these parts, and therefore these are the most important ones, I would say. And therefore I want to look into them. This will give us a feel of how this really works, how mathematical proofs work, how the logic behind this is working, and also to get a grip or a feeling of what math is really all about beyond the calculating, beyond the computing of some quantities. And the first proof I want to talk about is called proof by induction. So this is basically where you have some theorem, some statement, and you want to show by induction that it is true. So you start at one. This is most useful if you have something that is like depending on a number. So you have it, for example, formulated for some general number, and then you can use induction by basically saying, okay, I show first that it holds for the easiest case. For example, in most cases, if the number is 1, then I show that in this case it is the statement holds, and then you continue to the general case and show that it is true and then you basically have proven it. One example for this, where this can be easily applied or easily seen, is the Gaussian sum, or basically it's the story behind it is from Carl Friedrich Gauss, who was a mathematician, a really genius mathematician. And the story behind it is that when he was a child, in primary school, that he was that the teacher was asking them to, he told them to just count up all the numbers. So they should start by 1 to 100, and they should add them up each until they have received the result of adding all the numbers from 1 to 100 together. And the teacher, I think he thought to himself, yeah, this way I will can be at rest for some time until they have solved it. I have had a lot of time to relax or do something else. However, Gauss was a smart guy, so he, after several minutes, he had this problem solved. And the question is, okay, was he really a big calculator? Could he compute that fast, or what was his trick? And the trick was that he saw a pattern in this. So he was thinking of, or I guess he was thinking in such a way that he said, okay, I need to add the numbers from 1 to 100. Okay, but if let's say I take the 1 and I take the 100, I add those, I have 101. Then I take the 2 and the 99, I take those, I have again 101. I take the 3, I take the 98, and again I have 101. And so he figured that he just needed to halve the number up to which he needed to add the numbers. So 100 times he need to halve it, which would be 50. And then he would need to multiply this with this number up to which he needs to add the numbers plus 1, which is this 101. Because as he figured it out, in this sum there is a half times 100 times 101, because he takes these numbers in pairs, and these pairs always yield the number 101. And this way he could easily compute it, and the result is then 5050, and this he could compute in this way. And this is basically a formula which states that this sum of the numbers, of the natural numbers up to a certain part, is really this, if you say the numbers are added up to n, then this is n times n plus 1 divided by 2. And this is exactly what Gauss derived, and how he derived is in some sense proved by induction. So he started by saying, okay, I have this one case where I take the 100 and the 1, and there it seems to work out. And then he took the next case. Actually, this would not be the real proof by induction. It's some kind of induction, but actually proof by induction would basically mean in this case that you, for the n we had before, you take just one number and confirm that it's true. So let's say we have the sum from, let's make it completely easy and say we want to sum up to the number 1, and then okay, we have on the one side we have 1, and on the other side we have 1 times 1 plus 1 is 2 divided by 2, which would also be 1. So we see in this case it's true. So this was the first induction. Then we make the induction step and we show that this holds for general n, and this is kind of basically what Gauss did. And when we do this, we can show that this holds in general, and this is proof by induction. Another kind of making a proof is called the direct proof, where you basically conclude directly from the statement that you want to prove. You conclude this directly. You prove this in a direct way. An example for this would be the statement that if I have an odd number, so I have an odd number and I square it, then the statement is that the square of this odd number will also be an odd number. So any square of an odd number will also be an odd number. This is the statement that I have made. How can I prove this? So let's just look what an odd number is. An odd number is a number that cannot be divided by 2. So that cannot be divided by 2. It can, of course, be divided by 2, but then you would have a remnant, a residue, and so on. So, but you cannot divide it and get a clean result. Let's say it like this. And so I know that this is not possible. So how can I express an odd number which I would call n? I can express it in this way, that I say, okay, it's 2k plus 1. So k is some random number, and I multiply this number by 2. Then I have an even number, and then I add 1. So, and this will always be an odd number, of course. So any odd number can be represented in this way. If I, for example, take 3, then I can say the k is 1, then I have 2 times 1 plus 1 is 3. So any odd number can be represented in this way. And now I take this number and I square it. So if you know from school, if you know the binomial formula, then this is pretty easy. So this is basically if you have a plus b and you square this term, then you know that the result is a squared plus 2ab plus b squared. In our case, where we square n, which is basically 2k plus 1, there we have as a result of this 4k squared plus 4k plus 1. This is basically the result of our binomial formula in this case. And now, if we look closer into this, we see we have 4k squared and plus 4k plus 1. So we can take the first two terms and pull a 2 out of them. So we can rewrite it as 2 times, and then in brackets, of course, 2k squared plus 2k, and then plus 1. And then if we look at this squared part as an own number, then we again have this 2 times some number plus 1. And this 2 times some number will always be an even number, because 2 times any number is always an even number, because you can divide it by 2 apparently, because you multiplied it by 2, right? So we know this is an even number, and to this even number a 1 is added. So the resulting number will be an odd number. And there, with this we have proven that for an n, and squared, which is a number n, which is odd. If we square it, then the result will also be an odd number. And this is a way of directly proving some statement, which we have done now. This is a direct proof. And then there is a third kind of proving, which was always my favorite way to prove something. And this is the indirect proof, or also the proof by contradiction. And what you do there is you basically say you have some statement that you want to prove. And what you do is you say, I will assume that not this statement, but the opposite statement is true. I will just assume that, and then I will make conclusions from that, will draw conclusions from that, and will lead this to a contradiction. And if I manage to do so, if I manage to lead this to a contradiction, then this will automatically mean that the opposite statement, which is the actual statement that I wanted to prove, has to be true, because the opposite of it is contradictory, so it has to be true. This is basically the idea behind it. Where you can see this is a beautiful proof, also with a lot of history. It's the Euclidean proof, or Euclid's proof, which basically shows that there are infinitely many prime numbers. So the statement is this: there are infinitely many prime numbers. This is what we want to prove. So how do we do this? The way we do this is we just say, well, let's just assume that would not be the case. Well, if there would not be infinitely many prime numbers, then the amount of prime numbers needs to be finite. If the amount of prime numbers is finite, that would mean that there is a highest prime number. So there is a range, and then there's a highest prime number, and afterwards there are no prime numbers anymore. What we do now is we multiply all these finite prime numbers together, and clearly the number we yield will be higher than this highest prime number, because the highest prime number itself is in there, and it is multiplied by a bunch of numbers who are also prime numbers, and so the result will be a much larger, the number will be much larger than this. So in this area there shouldn't be any prime numbers anymore, because we are way beyond the highest prime number. Okay. What we do now is, or what we know now is, that this number that we now yielded is the product of all the prime numbers. This means it can be divided by any of the other prime numbers, and it will yield a result. So if I now add the number 1 to this number, what will happen then? I know that I cannot divide it by any of the prime numbers, because all the other prime numbers can be divided by the number before it, right? And therefore, I know that this has to be a prime number, because it cannot be divided by any other number but itself and 1, of course, and this is a prime number. This is the definition of a prime number, and but I assume that there are no higher prime numbers than the one I had before, which is way below that. So I know that this is a contradiction, that this cannot be the truth, and therefore I can conclude by this proof of contradiction, I can conclude that there are infinitely many prime numbers. So I hope you could follow these proofs, the thinking, the logic behind it. If not, I really recommend you to just take a piece of paper and write it down. Maybe also look something up on the internet if you could not follow along completely. Many of these proofs are pretty general, and you should be able to find them. And then write it down, and then oftentimes it's really easy to get the idea, to get the gist of it, and to then understand what is happening there. And if you really are interested, I encourage you to do that. But I hope you could at least understand these different techniques of doing proofs, of proving something, and also see the elegance of it, the elegance of the one or the other proof. And there are really, really elegant proofs. If you learn to study mathematics, if you dive deep into that, there are really is a lot of elegance oftentimes included. So there are some proofs which follow really a strict logic. For example, if you are studying linear algebra, there it is really, you go from one step to the next, follow them logically through until you have the wanted result. Some proofs really require a trick. You need to know something, or you need to have an educated guess or something, which you would not get by just following logically the steps. You need to just make a guess, and which is a good guess, and with which you can show this. Then this is more if you are in analysis, if you are in this area, differential. Calculus and so on. There oftentimes these kinds of proof are more dominant, but either way there's a lot of elegance in these proofs, and to prove such things that are really, you need to really be smart, or people who are able to do these hard proofs are really smart people. And if you need to also understand, this is most of the times, especially if you have higher mathematics courses and so on, the proofs of this, they are not just 3 lines of something, from A follows B follows C, so I prove this statement. Oftentimes they are really long, and in some math lectures, the whole lecture was basically just around one statement that needed to be proved, so that you can spend a lot of time on this. And some proofs, as I stated, they require different statements to be proved first, with which you then can prove this statement. So there is a lot of work going into it. There's a lot of it's a huge part of mathematics. And also, as we will see in a later episode, there is also a lot of proofs that are not yet done, where they are still open, where we are still looking for a solution, looking for someone to solve these. And this is still a high priority, because any statement that you make in mathematics, of course, it has to be proven. You have to know if it's true or not. And I think this is not only this kind of logical thinking that you learn there, because mathematics is basically logical thinking. You can state it this way. It's a way to think logically. And this is also what you learn in mathematics. You learn to think logically, to make logical assumptions and so on. And I think this is not only helpful in mathematics itself, it is also helpful in our everyday life, because in our everyday life we are confronted with all kinds of things where we need to think logically, where we need to try to understand things in a logical manner, try to make conclusions from it, try to get the right reaction, the right statement of this. And therefore, for this, we need to think logically. And this, therefore, maths is there a great help. For me, it also always was a great help when I was struggling with some problems or some things. It was always a help to think logically through the problem. Of course, in our everyday lives, it's sometimes more complex. Only pure logical mathematical thinking will not guide you all that much, or will not yield you to the every time yield to the end result, but it can be of great help, I found. And also, it is also if you are struggling with questions of faith and science, how this can be combined, for example, which we are talking on this podcast many times, or different issues. I found it that if you apply this method correctly, if you apply it consistently and correctly, then you can even get solutions to these problems, logical solutions, where you really understand what the issue is and can find a solution, can even find a proof or some kind of proof given the assumptions that you have made. And therefore it is a really helpful tool also in our everyday life. And I think it shows also that there is something beyond just the mathematical part of it. Because what you have seen is we saw that every time something contradicts, or every time you can lead something to a contradiction, then you know that this is not true. So we can see from this, we can conclude from this that truth cannot contradict itself, which is it might seem an apparent statement, but I think it's an important statement. And even in your everyday life, if you see something where you see that actually contradicts each other, then you know this cannot be the truth. And you know that true statements need to be non-contradictory. And also in mathematics, we shortly talked about definitions. Definitions are also really important, and it's important that the definitions are really clear, that they are well defined, which means that they exist and that they are unambiguous. Because if they are ambiguous and you cannot really say what this definition means, it's worth nothing. And therefore also, if you in your everyday life, if you have issues to discuss or to struggle, it's oftentimes it's important to make the definitions clear, to make clear what is your premise, what are you talking about, to get clear conclusions, because sometimes we are just don't get to a point because you have your premise not clear. You are not talking clearly about what you are talking, basically. And this can also be a great help. And I think it also shows in a deeper level. I mean, as I said, it's basically logic. Mathematical proofs, this is basically logic. And if we look into scripture, not in First John, in the Gospel of John, it says in the beginning that there was the Word, and God was the Word, and the Greek word that is used there is the logos, and there is already this logic is already included in there. So I think this logical thinking, also the fact that we can think logical and that we can understand nature in our minds with this logic, I think this is shows already that we are in fact created in the image of God, who gave us this logical thinking to understand his creation, and I think also to understand him. I believe that we cannot understand God by our human logic alone, but I think it can be helpful. It can be a helpful tool in our way to understanding him, in our way to understand scripture and to understand what he is telling us. And I think what we see here is that he has put his image in ourselves, and also that this logic, that this mathematics, which basically is the language of all nature, that this is basically his word, that is this is how he created his word, that we can see a glimpse of him there. And it shows also that the question why we can understand this universe is also oftentimes, and I will do later something on this topic, and I already have done to some degree, but I will deepen it again. And this is a huge question. I think we can understand why that is if we know that there is a creator who created also this logic, and who also has put this in ourselves, in our understanding, that we are able to understand it. And I think if we also, as we had it with the scientific method, when we are talking about this, we were talking about how Newton got from the theologians, from the natural theology, which he basically consumed and was taught on, which basically led to him to formulate his axioms and basically found modern science and the scientific method, that this was the basis of it. And we can also see, if you just look at universities, in the beginning they were basically founded because theologians needed a way to basically create canon law, to interpret scripture and so on in a logical manner. They did it in a logical way. They also found proofs of God, given certain assumptions, certain axioms, and so on. So there was a logical structure in theological thinking, and thinking about scripture, thinking about the word of God, which basically led to university and these institutions to come into existence. And this then led to people like Newton, who were inspired by this, to really come about with this natural sciences, coming from natural theology to natural sciences. So if you see there, this strain of thought basically came from scripture, from this logos, to this logical thinking, the logical mathematical thinking that we know of today. So I think, of course, mathematics has been around before. It's not that basically the Bible invented math. That's not what I'm saying, but I think some part of this, you can see some roots of this are in scripture, are in the Logos, and you can see it if you just see this connection from theologians and the first universities up to Newton and the founding of modern science. Episode 46, P versus NP, the $1 million problem. In the last episode, we were talking about mathematical proofs, and I also mentioned that not every proof has been taken, so there are still open issues. There are statements where we are still looking for a proof, or statements where we are not sure if it's true or if it's not true, but where there's still a proof needed to really make this clear, make this apparent. And today I want to talk about such a problem that is really still an open issue, where there is not yet a solution, there is not yet a proof that has been given out. And this is also one of the millennium problems of the Clay Mathematics Institute, which basically at the beginning of the millennium, they gave out some things that are not solved yet. I think it's about 7 issues or something that have not been solved yet. And among those is the problem we will talk about today. And they did not just mention these problems, but they also have a award money that you get if you solve them. So if you solve one of these problems, they will pay you out $1 million, basically. And there is only one of these issues that they stated has been solved by now, and that's the Poincaré assumption, basically. And this has been solved. I will not dive deeper into what this exactly is, but the funny story behind it is, so a Russian mathematician has solved this issue, and they tried to give him the prize money, but he rejected it. And also he received, or he was they wanted him to receive the Fields Medal for his work on this. The Fields Medal is basically kind of like the Nobel Prize for mathematicians, and is also connected with a lot of prize money. And they also wanted him to award him this Fields Medal, but he rejected that too. So interesting fella. But the other problems are not yet solved, and for the problem we will talk about today, which is P versus NP, this is also not solved today. But there's currently also a lot of work going into the trying to solve this problem, and this is an issue out of computer science, and there it is the case that there are certain problems that a computer can solve. But there are many problems a computer can solve, but the question always is, how fast will he be able to solve it? So let's say you want to, for example, sort a list alphabetically, and then you can ask, can give an algorithm to your computer, and he can solve it. But depending on how good your algorithm is, this can take rather long, because there are different kinds of ways to do it. And if the way to do it is really inefficient, then it might take a lot longer than if you have a really efficient and sophisticated algorithm with which it might work a lot faster. Therefore, you need not only to distinguish between problems that you can solve with the computer, because there might be problems with which you can generally solve with a computer, but if there are a huge number, if the problem is bigger and you need to solve for example, sort a huge list, and the computer can only solve this in a certain time, and then if the list is too long, then basically the computer will take, for example, weeks to do that. Is not a case for any computer for a sorting algorithm, but just as an example, if this is the case, then it is useless to you that the computer is able to solve it if he takes too much time to do so. So therefore, it's not only important to know whether a computer can solve a certain problem, but it's also important to know in how much time he will need, depending on how many entries or how much you give in to this computer. And then there is this distinction between algorithms that can solve a problem in polynomial time. So if you know from mathematics, a polynomial is basically something which goes with some potency. With, for example, x squared would be a polynomial. A simple straight line x would also be a polynomial, and there are different degrees. You can go to the third degree, x to the third power, and so on. And these are basically polynomials, and they, if they're what it means if an algorithm can solve a problem in polynomial time, this basically means that if you have x number of steps or x number of entries, then the algorithm can solve them in this polynomial times the length of your list, for example, steps or calculation steps, because that's basically what in a computer makes the time, what the steps of computation. So how many computation steps does the PC or the computer need? This tells you how fast it will be, because that's what a computer does. He does one calculation step after another, and if he needs too many steps, then even the fastest computer will be slowed down by the many steps that he needs to take. So this is the first part. This is basically P, what the P of P versus NP. This is the set of problems that can be solved in polynomial time. For example, it could also be that there are problems that are only to be solved in exponential time. Then this would be much harder, because if then the set gets really big, then of course this will take really long, because exponential means exponential. So it's really it's scaling really fast. But for a polynomial, the scaling is not so fast, and therefore if something is solvable in polynomial time, even if it is a polynomial maybe to the degree of 10 or something, it's still manageable for a computer in a reasonably amount of time to solve it. That's the idea behind it. So that's what P is, and now we need to ask what NP is. And NP is the number of problems where you can, if you give a solution, and you want to verify the solution. So in this, you have an algorithm that can verify if to a certain problem, the solution that you propose is really a true solution. So, for example, so there is this mathematical rule that every number can be factored into prime numbers. So you can have, for example, if you have the number 6, you can factor it into prime numbers, into the number 2 and 3, which are both prime numbers. And if you multiply them, you get the number 6. And this you can do with any number. Maybe you will have more than 2 prime factors, or maybe you will just have one if it's a prime number itself, of course. Or you will have a lot of prime factors, maybe the same prime factor also several times. For example, if you would try to factor the number 8 into prime factors, you would just take 3 2s. 2 times 2 times 2 would be 8. So, and this we know is possible. So there is a unique set of prime factors for each number that there is. This is could be mathematically proven. We know that this is the truth, and it's however, there is no computer algorithm which can do this in an efficient way, so which can do this in a way that it is happening in polynomial time. So we know of no algorithm which can do this. So to factor a number into their prime factors is not possible in this way. However, what is possible is that if I have the prime factors, if I know the prime factors, or if I think I know them, and I put it in a computer and I say, check if these prime factors manage to get this and that number. then of course this is just a simple calculation, then the computer can do this. And therefore NP are the problems for which this is fulfilled in polynomial time. So in there you can basically compute can verify a certain solution. This is basically what NP is. So what we see from there is that P is already part of NP, because since P is the number of problems that for which you in this polynomial time can find a solution, if you can do this, then you can surely also verify a certain solution, because you can find the solution itself, so you can also verify any solution. So P has to be part of NP. So this part of the question is already solved, because the question is whether P is equal to NP. So the question is whether it is possible for every problem where we can, if we have a solution where we can verify it in polynomial time, the question is if all these cases where this is the case, if we can find an algorithm which would solve these problems in polynomial time. So can we find, for example, an algorithm which would be able to find the prime factors of a certain number in polynomial time? Would this be able? Does the fact that we can verify a solution or verify for certain prime factors that it is indeed that these are indeed a prime factor of a certain number, does the fact that we can do this in polynomial time also mean that we can find an algorithm that will get us the prime factors of this number in polynomial time? This is basically the question, whether P is equal to NP. And as I have said, we know that P is part of NP, so we know that this one direction is already holding. So we only need to show if the other direction is true. If we given a problem in NP, if this will also be a part of P, if given that we can in polynomial time confirm a solution to a certain problem, whether this also means that we in polynomial time also can find this solution to this problem directly. This is the big open question that mathematicians and hobby mathematicians try to solve and are researching on. And up to now, they could not find a proof. And the assumption is, of course, that this is not the case. So the assumption is that P is not equal to NP. And I think if you could follow what I was telling you, if you could follow the logic of this problem and understand what this is about to some degree, you might also have this intuition that that is not true. I mean, just because I can given a certain solution to a problem, and just because I can verify it with some algorithm, that does not mean that it has to be a kind of equally efficient algorithm which can solve the whole problem itself. That does not necessarily need to be the case, right? So that's just intuition. It might as well be true, but right now the assumption is that it is in fact not true, that P is not equal to NP, and that's the state where it is now. But until there is no proof of one or the other, until then it's basically we cannot say what is true, which way it is. We cannot really say this for sure. So the question is, why is this important? Is this just nice reasoning? Is this just fun for people who like to do proofs, or is this just to give $1 million to people who are pretty smart, or something like that? Or is there something behind it? And actually, there is something behind it, because most of our encryption systems are based on such things. Because I was talking about the prime factor factors, that every number can be separated into prime factors, and this is highly used in encryption systems because they use the prime, they know the prime factors of the number that they have, and from this they use this to encrypt in a certain way. Don't want to dive into the details, but what the fact is, if it would be possible to put this number into its prime factors in a direct way, so if you could show that this is a problem of p that is solvable in polynomial time, then you could basically hack most of our encryption systems. You could basically go around most of these security algorithms, because you could what they are relying on is that with the current algorithms, to put these numbers in their prime factors will take a long time, since these are not just small prime numbers, these are huge prime numbers, and therefore it will take a long time, much longer than it would be reasonable. So we are talking about years or even thousands of years here, because the algorithms to solve this are just not that efficient. But if you could show that there is an algorithm which is much more efficient because it runs in polynomial time, then this would be a real problem, because our security system would then be really fragile, because as soon as somebody would find this algorithm, he could basically hack all the systems in the world, basically, as I understand it. So, and there's also these other things. There are these one-way functions, basically, what they are called. So this is if you type in your password somewhere, or if you are logged into somewhere and you type in your password, they, of course, in some sense, they need to store your password to know if you type it in, if it is correct or not. But actually, that's not really what they do. So they don't, on their servers, they don't write in your password in plain text for everyone to read, basically, because that would really be really dangerous. But what they do is they hash your password. That's what it's called. So they have this function, which is a one-way function. What that means, it cannot be turned around. So they can, from your password, they can create this hash, but from this hash, it is, at least that's the assumption, that it is not possible from this hash to create your password. So to reconstruct your password, this should not be possible. So what they do then is they have this hash of your password. This they have in their servers. They also put some other things above it to make it even more secure, but that's another story. And once you type in your password, what the server does is it immediately hashes your password, goes into the table with your password or into the database, and confirms the hash it has there with the the hash of your password. And if they agree, then he knows, okay, you seem to be the one who knows the passwords, you seem to be the right person, and then he basically lets you access. One problem with this is that in this one-way function, it is not clear that that this will always yield an unique result. So in principle, it could be that there is a different password which would yield the same hash as yours, as the hash of your password, and therefore this could get difficult, but it's really unlikely that this happens. So it might be, but probably it's not the case. But also what's not clear is if this is really a one-way function. So there is no clear proof that these functions that are used there, that they are really one-way functions and that they cannot be turned around, because if p would be equal to np, then these one-way functions could not exist. So if one could show that p is equal to np, then one knows that it is in principle possible to reword these functions and basically from the hash restore your password. So the fact that, or this let me say it like this, you better hope that p is not equal to np, because if it is, that would mean that we would need to think of a whole lot of new security systems, because our current security system would all be compromised, and it would only be it would only take somebody to find the correct algorithms to hack them all, to get into all these systems. So I hope you could get some idea about what this P versus NP issue is. And if you are excited now, you can try to solve this problem yourself. As you have heard, there's a lot of money to be won if you manage to do so. Okay, time for a short break. This time I will not read an excerpt from my science fiction novel Alien Thoughts, because there are great news. For if you are an English listener or only English-speaking listener, then this might not be that big of a news for you. But I wrote a new book. It's a crime novel. It's also about topics like software development, open source, and so on. However, it's right now only in German, and it's also part of some competition where I could hand it into some publisher in Germany, and if it gets really well, then I will I might be able to receive an award or something like that if I'm really lucky. But still, it's currently published only there, and therefore also the rights are of course only there. So until then, I cannot publish it otherwise, also not in English, I think at least. But just to keep you informed about what's going on, and this is the book is called The Odysseus List. Also, this is a pun in some sense, so I'm not sure when I translate it how I will resolve that. But if you are a German speaker, or if you can understand the German language, then I really encourage you to get it. It's in Thalia. You can get it there. You can order it as a print book. There's no ebook yet. So if you are fluent in German, then I encourage you to read it and to order it, and to also write a review, because this is always helpful to me, and of course also for the competition itself. So if you are interested in this, then check it out. It's called Die Odysseus Liste. And as soon as there is a development in getting this book out in English, you on this podcast will be the first to get to know about this. Episode 47, What does the inside of the proton look like? On this podcast, we several times talked about the fact that protons and neutrons are not elementary particles. Elementary particles in the sense that they are point-like particles, that they have nothing which they consist of, but are elementary in the sense of being really the elemental parts of matter, which is assumed for electrons and other particles, but for protons and neutrons, we do not believe that it is the case. Actually, we know that this is not the case, because we know that they consist of different particles, which we call quarks. And usually one says that particles like protons and neutrons consist of 3 quarks, but actually those are only the valence quarks. And in this episode, we want to talk a little about that, a little bit about how much more complex the proton actually is, but also much more beautiful, I think. So when we found out, or when in particle physics it was found out, that protons and neutrons are not the elementary particles, but that they consist of, or that they have a substructure of particles inside of them, these so-called quarks. Of course, this had to be confirmed doing measurements, and the measurements that are still used to show this are particle accelerators, where particles are accelerated to huge speeds close to the speed of light, and then they are collided with each other. And in these collisions, a lot of things are happening. New particles are created. These particles interact with each other. And with this, we can really find out about how these particles do interact with each other. But we can also find out the structure of the particles that we collided. So, I mean, of course, there are also electron-electron colliders. There we will not find out a lot new about the structure of the electrons themselves because they are point light particles, so there is no substructure or nothing beyond them to find it. But at the LHC, the Large Hadron Collider at CERN, for example, they are colliding protons, so we can learn a lot about this substructure by these scattering experiments, and this is also what was done there. And we also need to keep in mind that the higher the energy is, so in particle physics, higher energies always mean closer distances. So the higher the energy is that I use, the closer I can look to the particle. This is basically the rule there. And so the higher the energy, the more we are able to resolve the substructure of protons, neutrons, and other particles. And what was shown there is that the distribution of these particles is not flat, but for point-like particles that would have been to be expected. So we even saw there, okay, it cannot really be that these protons consist of only these three valence quarks, because then we would have had this kind of flat distribution, which we did not have. So we knew there had to be something more going on. And there it was introduced a scale, which is called X. And this scale basically tells us how much of the momentum of the proton is in the specific valence quark. So how much of it, which percentage, so to speak, is in this, of the momentum of the proton is in this valence quark. And you might expect, you might say, okay, we have a proton, we have three valence quarks, so I would assume that about a third of the momentum of the proton is in each of these valence quarks. Maybe one has a little less than a third, but then the other therefore has a little more than a third, and altogether it yields the complete momentum of the proton. That would be the idea, right? However, this is not what we see. So especially to higher energies, we see that the valence quarks have much less than a third of the momentum of the proton, and this is all of them. So you might even think, okay, is momentum not conserved anymore because they don't add up to the whole proton momentum, or what is happening here? So what is this scale violation? How also the scale X, which basically shows the amount of momentum in these of the proton in these particles, how is this so violated? How can this be? What is the reason for this? And the reason for that is that a proton does not consist only of these point-like valence quark, but that there is a sea of particles that through splittings and mergings of gluons is created. So we have learned that gluons are basically the same thing like light is it's the same thing for the strong interaction, like light is for the electromagnetic interaction, or photons for the electromagnetic interaction. And this is basically what the gluons are for the strong interaction. And they can be radiated from the quarks, and then they can themselves decay into quarks, or radiate other quarks, do all kinds of stuff, more even so than the photons, because the gluons themselves carry a charge, which the photons do not. So there's a lot of things going on there, where the valence quarks can radiate gluons. These gluons can create other quarks, which are then called the C quarks, because actually in this proton there are not only these valence quarks, but there are a bunch of other quarks which are called the C quarks, that are just created in these kind of fluctuations and so on. And therefore, the proton is basically not just some three-particle structure, but it is really a structure of a lot of particles that are flowing around there, and depending on how much momentum it has, this even increases. So for high momentum, high energies, it is the case that basically the valence quarks only make up a small amount of the momentum of the proton. If for high energies, the most amount of the energy is in the C quarks and the gluons. So I think at high energies, it's mostly, you can basically assume that the proton basically only consists of gluons anymore, because there is so much momentum in there. And also in the C quarks, for example, there I think at some certain energies, it's just like more than 50% of the momentum of the proton is in the C quarks and so on. So it's not just these 3 valence quarks that are flying around there. There's a lot more going on. And this is also described by so-called Proton distribution functions. They basically describe all these things, how much momentum is in the gluons, how much momentum of the proton is in the C quarks, how much momentum of the proton is in these valence quarks. And you can see this in these distributions, especially at lower energies. You can see the peaks at the up and down quarks for the proton and the neutron. You can see the peaks there, but if the energy increases, there's more and more a general peak at the C quarks and gluons, because they begin to dominate the proton's momentum. So these Proton distribution functions, by the way, they are not calculated. They are measured at the LHC, and the LHC uses this to know at which energies how huge the part of the momentum is that goes into the valence quarks and that goes into the C quarks, because as we have seen, the problem that the LHC has to deal with is that they do not only know the momentum of the protons that they are colliding, but they don't know so much about the momentum of the actual particles that are interacting, the quarks and so on. They don't know their initial momentum, which makes it much harder to really make these computations, to analyze the results, and therefore they need these Proton distribution functions and these scale X to really know what particles are present the most, where the momentum of these particles is. And this scale variable X is oftentimes also called the Bjorken X. And this is named after theoretical particle physicist J.D. Bjorken, who recently died. So this August, he died at the age of 90. And he was really really great theoretical physicist. He was behind these Bjorken X variables, so he introduced this, and also he came up with together with Clashow, he came up with the idea of the charm quark, because I'm not sure if I have mentioned it on the English podcast, but it is the case that as we have seen, protons and neutrons consist of quarks, and they consist of up and down quarks. And so this, for a long time, or for some time, this was the only quarks that we know. So we thought, okay, they are up quarks, they are down quarks, and basically protons and neutrons and all the other hadrons consist of them. But then we found hadrons that are not seem to have different quarks in them. And the one quark that was first found was the so-called strange quark, because it was named this way because it seemed strange that there is a particle that is a quark that is neither an up quark nor a down quark. So this seemed really strange until they had the idea, okay, maybe these quarks come in families, kind of like the leptons come in families of electrons, muons, taus, and maybe the same is the case for the quarks, and they come in families. And so they postulated a charm quark, which would, in a charming way, close this gap, or close the thing that they had there, the issue that they had there. And this was what Bjorken and Clashow postulated or introduced also, and this particle was then indeed found. So I think Bjorken was someone who was, I think he was also sometimes recommended for the Nobel Prize, but he never won it. And he was still a brilliant physicist, and I had also the pleasure of being in a talk of him once. So he was once at our University of Heidelberg. He was giving a talk, and this was several years ago. I mean, he was already past 80 then. And he was basically in his retirement, and basically was talking to some degree, in some part of his talk was about what he all experienced, which physicists he met, Pauli, Feynman, and so on, and how his life as a physicist was like, and so on. And also he talked a little bit about things he's interested now that he's retired, because usually he was as a physicist, you only do stuff that is in your field, as you are pretty specialized in your field, and oftentimes you are the only expert in this field, but you are not observing other topics oftentimes. And once you get in retirement, many use this to also look into the different topics that they might be interested in. And he was talking a little bit about that he is looking into general relativity and stuff like that. And what was also interesting then is that the question came about what he thinks of string theory. And he mentioned then that he thinks this theory is a pretty powerful tool chain, the tools that it gave to mathematics and so on. But he was also critical of it being considered a theory like the Standard Model or similar theories, because of the lack of proof, the lack of confirmations or verifications, as we have stated in our episodes to string theory and so on. And he even brought this comparison where he said in the US it was basically forbidden to teach creation science or creation in science, because it was said that the creation theory or theories of creation don't hold up to scientific standards, and therefore it would not be right to teach them in science classes. And this was the argument brought forth then. And Bjorken compared this to string theory, where he said that this also does not hold up to these standards of verification and so on. And therefore, he emphasized that he thinks it's a powerful tool in some sense, but he does not believe it to be a theory comparable to other more successful theories. And the interesting part is, as I knew from the professors that I knew, there were many professors in this talk who were working on string theory and who were pretty passionate about string theory, and to look in their faces was kind of amusing at that time. But I think he was not impolite, he was not dissing them or something. He was saying in a polite way how he thought of it, and I think it's an opinion that is pretty common among scientists who are critical of string theory, and therefore this was nothing that they did not hold a grudge against him. They understood where he stood and what he was saying, but still they of course weren't amused about it. But I think this was pretty interesting. It showed also the differences that are there in science among scientists. But it was a pretty interesting talk, and he was to me he seemed like a really nice guy. Episode 48. Is it all Linux or what? So in this episode, I want to talk a little bit about operating systems. That's just because in recent years, I work as a system engineer, so I work more in the technical area and the engineering area. And therefore, I am also much confronted with operating systems, also in my private life. I switched from one operating system to another, basically, and can now say that I'm pretty experienced in almost all of them. That's why I think can talk a little bit about that. And I think there are interesting ideas behind it, and there's an interesting... Today I want to talk about an interesting concept in the author where we can also learn a lot about faith, or we can basically see it as a as a parable to faith, because as I have also mentioned, because I mentioned also before about this pseudo command and the power that is in the name of Jesus. So there I had also this parable of this technical concept and how this is done in operating systems, and how we can see this as an parable to the power that is in the name of Jesus. So this I found really interesting, and today I want to do a similar thing. It's not exactly the same, it's a little bit different, but I think it's a showing way to see how something really is significant in this world, which we all already discussed on this podcast, and therefore I want to point this out. And this example of operating systems is really helpful there. But first of all, I want to in general talk about these operating systems, what the differences is, why I like the ones more, the others less, and so on. And also, I think it gives some insight. So if you tend to read my new book, which currently is only in German, then this would also be delivering some insights, because in this book it's also about operating systems, it's about open source and these topics. So if you want to learn more about this, then this episode might be the right one for you. And even if you do not intend to read a book, I think it's good to learn about these operating systems since we use them that much, and also about what we can learn from this parable. I think it's a pretty beautiful parable, but that this we will see later. Because why I also dive so deep into this is also because I might in the future do several episodes that go more into this technical direction, where I will more talk about things like operating systems, coding, and so on, depending on whether it fits with the general topic of Sci-Faith, whether it fits into that premise, then this might be the case, and therefore it would be of course nice if there would be also already a groundwork laid in there. So let's just start with this. So there are basically 3 operating systems. You can mostly all operating systems are in some sense can be related to one of them. So there's of course Windows from Microsoft, which is the most predominant in the desktop space, but we will get to this in a bit. Then there's macOS or iOS from Apple, and of course there is Linux, which is open source. So what is the difference between those? So let's first look into Windows. I already mentioned that it is in the desktop space or desktop PCs and so on, that's the most predominant. So it's commercially really successful, and the software and the operating system is proprietary. What this means is that the code, the source code of the system is not open to the public. So you could not look into it. Even if you buy it, you cannot see the code. You cannot read the code, how it is set up and so on. You just have to trust that the engineers knew what they were doing and that they do not mean any harm to you. And then you can install it. And if everything works fine, great. But that's basically what it is. I never really liked Windows, to be honest. It's especially years ago when I started to use a computer, it still was very buggy. Today that's less the case, but today there are still some things, some bugs in there, and also some bugs where you might say, or some bugs who are not corrected because they seem to them or to the people who develop them to be a feature. For example, to this day, I cannot understand why when I shut down my PC, to me, if I press shutdown on my PC, that should mean it shuts down no matter what. But this is not the case. There are certain programs that for no reason at all can just stop this shutdown process, and every time you shut it down, you need to just wait for it to tell you whether you really want to shut it down. And funny enough, if you would click no, I really want to let it start it up, most of the time it still shuts down, so there is no reason for this at all. But if you just leave your PC and this question comes if you want to shut it down or not, and you are not there to answer it, then it will just go into standby mode, which is not doesn't make any sense, especially in times where they are so far that they can basically anything you do not save, they can save it in some temporary folder, and if you start up again, you will have your results back. So there is no reason for this feature, and therefore I really don't understand it. I don't like it, and that's why I was never. And I think the other operating systems do it sometimes also, but not in this extreme way as I have experienced it with Windows especially. So therefore I never really liked it, and for a long time was therefore a user of macOS. macOS is, as I said, operating system of Apple. It's the, I think, second most used desktop operating system, or for operating system used for desktop PCs. And it has some similarities with Linux, as we also have seen in the episode to the sudo command, because both of these systems can use these sudo commands, which Windows can't. And therefore there are some similarities because they are kind of based on the same ground system, which is Unix. And but macOS, in contrast to Linux, is also proprietary. So there are some open source parts of this of macOS, but most of it is proprietary, and therefore similar to Windows, you do not really know or cannot really see the code that is used there. You cannot really see the source code and so on. And what's also there is that what made me be less and less excited about macOS was the fact that they did not give you did not allow you much choice in how you want to configure your system, which in the beginning wasn't really a problem to me, because most of the things they gave you, most of the configurations they gave you were pretty good in my opinion, and therefore I did not have the urge to change them. But in recent years I think this changed pretty much, and more and more they really did not let you change it the way you wanted it, and therefore I began to switch to Linux. And Linux is the only of these systems which is open source, so you can really look into the source code. You could online check the source code. How does this operating system work? You could see all the lines of code. You even could participate if you are somebody who knows one thing or two about operating system. You could even contribute to the code, and of course there is a checking mechanism. Just because you pushed your code in there doesn't mean that it will end up in there. There will people who will review it and so on and so on. But if you are a good developer, you could in principle even contribute to this code. And this is basically what open source is all about. And this is also the reason why those are basically the only three operating systems, because Windows and macOS, they have been around for basically forever, and Linux came a little bit later, but it was from the beginning it was open source, so nobody right now would say, okay, let's code our own operating system, because it's a lot of work. And why do you need to reinvent the wheel? Why do you need something to do something again if you already have done it? It would only be necessary if all the systems were proprietary and you could basically not use them because they are closed. But since there is something which is open source like Linux, you can just basically take this and use it for your own. Of course, there are some licenses that prohibit certain kinds of uses or limit the way how you can use it. But most companies have found a way to deal with that, and therefore most of the operating systems which are not Windows or macOS and which are produced by some company for some device or something, they are in some way some kind of Linux in the most cases. For example, if you just look what Google does with the Chromebooks, this Chrome OS is basically some kind of a Linux distribution that they configured in their own into their own preferences, and this is basically how it's done today. And also there is not this one Linux. Linux is basically just the kernel of this operating system, and there are many different variants of it. There are many different distributions, like there's Ubuntu, there's Debian, there's Arch, and there are hundreds of other distributions that are there are some core distributions like Ubuntu and Arch and so on which many other distributions are based, but there are also there are a bunch of distributions who really some of them only have some changes in the desktop interface they use or something like that, but there are really a lot of these variants. Which brings us to the next point. As I have said, what I did not like about macOS in the later years was that you really could not configure it anymore to your own liking. With Linux, this is completely possible, but it is not only possible, it is necessary. So you can configure everything yourself, but this also means you need to configure everything yourself. So you need to set the system up completely to yourself. So while if you have Windows or macOS, for example, and you just install it on your computer and then you can start right away, you don't need to do a lot of configuring stuff. But for Linux, you would need to do this. So you need to make some configurations here and there till you have a system that fits to your needs. But I can say so, at least for my own liking, it was really worth it to take this and to really configure it in this way and take the amount of work that it took, because in the end, to me, it was worth it. So this was basically an overview about these operating systems and what I think of them. Now I want to come to the point that I actually want to talk about, and this is if you just look at these operating systems, and let's say you look at a statistic, okay, how many of these operating systems are used on personal computers, on desktop PCs, how many of them are used, which is the widest used and which is the least used. And you will find that Windows is the most used of them all. And then the macOS has also a certain amount of usage, but Linux on desktop PCs is almost not used at all. So it's a few percentage points that are there, but it's really small, a really small contribution. So you might be tempted to say, okay, almost nobody is using Linux, right? So almost everyone is using macOS or Windows. Linux isn't used at all, so it's just not needed. I mean, okay, those few nerds, they can have their Linux distribution, but actually you don't really need it. And though nobody ever uses it. Nobody uses Linux. And this is where you would be wrong, because as I said, companies and people who produce devices that use operating systems, they do not like to reinvent the wheel, and and most of the time they just take a Linux system and put it in their devices, tweak it to their needs, and then use it this way. And this is in most of the devices that require an operating system have some kind of Linux installed on it. Also on servers, so in the internet, the servers are mostly running on Linux. So if you access the internet, most of the web pages there will be running on some Linux instance. So therefore, it is not the case that it is not used. It is used a lot, and each of us is, without recognizing it, using it a lot in our everyday life, because it might be hidden, but it's integrated in almost everything we use. Most of the internet is running on AWS, Amazon's web services, many web pages, Netflix, and so on. They are all running on this AWS, on these server platforms, and this is running on Linux. And also social media and so on. This is most of it, I guess, is all running on Linux. So every time you log into somewhere on the internet, every time you start your smart TV, which is most likely, if it's not an Apple TV, it's most likely also running on some kind of Linux. And even if you have an Android phone, Android is also oriented on Linux. There are some changes, and also in the licensing of these changes that are such that it is not completely open source, but it's still in some sense Linux. So basically everywhere where you do not directly use Windows or macOS, you can be pretty sure that it's most likely Linux which is at work there. So although you might not be using Linux as your desktop PC, Linux in your everyday life where you see, oh yeah, that is Linux, you use it all the time when you access the internet, when you put on the infotainment system in your car, when you have a fancy coffee or cooking machine which also has an operating system. In most cases it will be Linux that is running on there. So what I want to say with this is, I think it works the same in the spiritual. I think if we look in the spiritual, as we have mentioned already on this podcast, this book of Tom Holland, Dominion, where he talks, so Tom Holland is an historian, and he talks about the influence Christianity has had on especially the West, and how things that we would consider to be completely that we would not question a bit, that we would not question a second, where we would say, yeah, it's completely clear that it has to be this way, that we have to, where we did not even question the thoughts that they are so obvious to us, but the root of these lie in Christianity. And this he argues a lot in this book Dominion, where he basically tracks down the roots of our convictions today, how they came about, how they came out of Christianity, out of the Christian faith. And where today, if you look into the world, you might think, okay, let's look at the church numbers, people going to church. Yeah, it's not that many anymore, or something like that. That the numbers are decreasing. Yeah, people are losing their faith. It looks like in this world, at least. And you might say, yeah, okay, maybe faith is just not needed anymore. Maybe we have our convictions, which are pretty solid, pretty good. We don't need faith anymore. But you would be wrong, because all these convictions, all these things are based in this Christian faith, are coming out of this Christian faith, are coming out of the gospel. And I cannot dive too deeply into the details, but if you want to learn more of this, I really would encourage you to read Dominion of Tom Holland. There you can really get a glimpse of this. You can really see how our history evolved, influenced by Christian thought. So this is really interesting. And if you could also make the case, I mean, you could, from this image, as I said before, when you see, okay, almost nobody is using Linux desktop PCs, and from this you could conclude, yeah, if Linux would not exist anymore tomorrow, who would care? Nothing would change, right? And you would be wrong, because as I have said, many things in the hidden where you don't see it, they work on Linux. They use Linux as their operating system. And if Linux would be gone tomorrow, almost all of the internet wouldn't work anymore. Almost any device would not work anymore. There would be only several few devices which could still be working. So it's just not true that this would be the case. And I think in a similar way, it's just not true that a world without God, a world without faith could function properly for long. It's just not just because faith is something that it's some nice story that works good for people, and although there is no God, it just works out. No, that's wrong. It's because God is real and God exists, and this is shown by the fact that God, that faith has so many fruit that it brings forth, many good fruit that it brings forth. And as you can see from, if you take a fruit from a tree and let it stand there, it will get bad. It will get bad, and because it's removed from its source, it's removed from its root. If you take a flower from the meadow, you can put it in a vase, you can put water into it, and this will prolong its life. But after a certain time, the flowers will get bad. And in the same sense, it's here. If you remove these convictions, all these things, all these principles that we got out of the Christian faith, if you remove the faith which is on the foundation of it, which is at the root of it, if you remove that, then it will be just a matter of time until all these principles and all these ideas and all these ideologies and until all this will also become really, really bad. It might be a long time until this really happens. You might be able to stretch this process for a long time, kind of like a flower that you put into a vase with water to prolong this process. But in the end, it won't suffice to conserve it for a longer time. And for this, you really need to put it back into its roots, and this roots is the Christian faith. So if you hear this, and if whether you are a believer or whether you are not a believer, no matter where you stand on this, I really encourage you to ask a question yourself: which kind of convictions, which kind of ideas might be not ideas that I just have because I think, yeah, they are just there. Everyone thinks like that. Which of these might be coming from maybe the Christian faith, maybe the fact that you've been raised in a world that is deeply rooted in Christianity, that whose ideas, whose convictions, whose principles are deeply rooted in the Christian faith. So I would like to encourage each of you to try to think about where in your life this might be true, and then think about these principles, these ideas. Are they what they are worth to you? Whether you believe them to be true, and whether you believe them to be true, how you think you can make sure to conserve them or even expand on them even more to get even to a deeper level of truth, to a deeper level of understanding. And if you think about that, how can this be possible without the root of it? Without the root, which is God himself, which is the Christian faith himself, from which this all has stemmed forth. So I really encourage you to try to look deeper into that, because I think on one hand it's really interesting and fascinating, but on the other thing, I think it's on the other side, I think it's really important to understand this and to also see where our convictions and our ideas come from, because only in this way we can really sustain them and even expand on them and get on a deeper level of truth about them. So that's everything for today's episode. I hope you liked it and you enjoyed each part of it. If you want to get in touch with me or discuss a topic or want to give me some feedback, then feel free to contact me using the contact form on my website, sci-faith.de/en. And there you can go to the contact tab and contact me. And if you have any other things or episodes you want to have covered there, or topics you want to have covered, feel free to contact me there. Also, if you are not yet familiar with the format in which this podcast is produced, let me just briefly explain it to you. So there is always at the beginning of a month or of a block, there is a big block of 4 episodes in one thing. It's kind of like a preview, which I call it, where you have the next 4 episodes all in one episode together, combined. And this is for people who like to hear long format podcasts, who have a long way to work or something else, where they can listen to a long episode and can then have a preview of the next 4 episodes all at once, and are completely up to date from the beginning of the block. For those who like their episodes shorter, who prefer it if they have a half an hour or even less of a podcast episode, for those there is every week afterwards will appear a podcast episode almost in that length, and this way I can publish every week a new podcast every episode, and everyone can have it his own way, either once a month a long chunk of content, or once a week a shorter format podcast episode. So I think that's the best way for everyone, and also for me when I'm producing it. Please also note that this is an independent podcast, which means that it is recorded, produced, and marketed by me. So I really need your support in this. So if you like this podcast, then give it a 5-star rating. And if you have the time, even write a review to it. This just helps other listeners to become aware of this podcast, and then people who might be interested in this content can become aware of it. Also, if you have friends who you think would like this content, then recommend it to them and share it with them. Also, you can support me in other ways, for example by reading my blog and subscribing to my newsletter, or even by reading my books, which you can find on Amazon. For example, there is my latest novel out now is Alien Thoughts, which is pretty entertaining from the feedback that I gotten, and so it's also in some way related to science and faith. The topic of it is also in there, but of course you can also read the book to this podcast, Sci-Faith, The Compatibility of Science and Faith, which is also available in English since last year. Thank you for that, and now I wish you a wonderful day, and I'm looking forward for you to tune in again next time.